مرحبا طلاب. راح أكمل الفيديوهات اللي يعني بديت بيها، وبس أخلص أبعث لكم إياها إن شاء الله. Okay. This is a skill assessment problem for 4.2 first order system. I'm given, consider the system with a transfer function which is g of s equal for 50 over s plus 50. He wants us to find time constant, settling time, and rise time. Okay, just to remind you that this 50, this one, okay, it's A, okay, so that you know. Of course, settling time, time constant, we found it before in the previous YouTube, so when you see the YouTube, you will understand what I'm talking about. TC equal time constant equal 1 over A. 1 over the root of the equation. This is the root of the equation, the one in the denominator. 1 over the root equal to time constant equal 0.02 second. The settling time, we said it's 4 time constant. Look at this, it's 1 over A times 4. So it's 1 over A, which is this one, it's the time constant. So the settling time is equal to 4 time constant. We'll come into that a lot in this chapter. So it's 4 over A equal 4 over 50 and equal 0.08 second. Now the rise time equal TR equal 2.2. This is a formula we found over 50 and equal 0.044. And I told you before in the previous video that rise time always smaller than the settling time. This is our real infinity. We say that at infinity system will, the natural part would die away and we only have the forced part. This is like the practical infinity, the one which we reach to the final value. So look at this, this is the rise time, is smaller than the settling time. Don't forget that, okay? Now after the first order system, we'll go into second order system, then higher order system. I'll start with the second order system. This is section 4.4, second order system. In second order system and higher, we'll find the situation is different. The response is different. Here we don't have parameter that is changing. It's only one parameter, so it have a significant response in the first order. It doesn't change. So when you look at it, maybe when I go through again other examples and I go into details of second order and higher, I'll tell you how to distinguish between first, second, higher order system, okay? In a second order system, let's imagine that we have a transfer function like that, like a constant b, s squared plus as plus b. We have the output c, and we have r, that's the input, and we need to find the nature of this output c equal g times r. That's mean c equal g of s times r of s, as we said and as we all know, and changing the response, the type of response we get at the output. Let's say for a step, of course, we said that the step is a test signal we use to test the system. It depends on the value of a and b, okay? Once we change, if we keep one of them, let's say we keep, because it will be difficult if we change both, we keep b and we change a. As we change a, we see that the response will be completely different. Okay, let's see that. I have a table here from your book. It's on page what page? Don't know really. Section 4.4. Okay, doesn't matter. It's figure 4.7. Okay, he's putting this the transfer function which I put in the previous slide. I have an input which is 1 over s step, and the transfer function is b over g squared plus as plus b, and the output is c of s. I want to study the output c of s as one parameter, which is a now, is taken as the parameter which is changing. So now let's keep b at 9 as it is. We take a equal to 9. This is the first one. We found that we have two poles, two real poles. If I take that mean if I take s squared plus 9s plus 9 and factorize it, I'll get although they are I don't know, awkward numbers. They are minus 7.854 and minus 1.14. They are both here. Here they are. This one and this one. They are both real. Of course, negative is a stable system. We'll learn this, let's say, later. And if we plot the response and the type of response, here it is. One is for the step input and plus this part, this one 0.171, which is a constant e to minus 7.8 minus 1.171 e to minus 1.146 t. Of course, the one is the forced response. The second two parts, they are the natural response. We see that the one is fixed in all the responses, but those they change because we change the parameter. So the natural response depends on the parameter. Okay, people? Now, so here we have two real and different root or poles, and the response is doesn't contain any sinusoidal part, so it's real. Okay. Now let's change this A to 2. Instead of 9, let's take it into 2. So we get those two poles here. They are complex, minus 1 plus minus j. So here S will be minus 1 plus minus j جذر 8. Okay, here we have. Here is the 1 and here is the j جذر 8. So they are complex. Once you see a complex poles or roots, now you say that the response will be sinusoidal. But it's not a pure sinusoidal, it's exponential, damped sinusoid. We call it damped sinusoid. So this is the one, forget about this, is the input force response. E to minus t, let's take the second one, it's easier. 1.04 e to minus t cosine تحت الجذر 8 t ناقصا 19.474, and we'll learn later how to get all this by hand. Okay, but now just to explain to you the type of responses as we change the parameter. So this we called, it's a sinusoid, but it's a damped sinusoid. Now let's take this one, that one. This one is completely different. Why? Because we took away the 2s. So the A is 0. Okay? When the A is 0, this means that we have a system with 9 over s squared plus 9. The roots will be plus minus j3. This is 3. I don't know how I wrote it. So we have s squared plus 9 equal to 0. ينتج عندي s equal plus minus j 3 here on the j omega axis. Once we have a root on the j omega axis, and it doesn't have a real part, this means that we have a pure sinusoidal response. Look at it. This is the one for the step, and minus 3 cosine 3t is for this one. This system is not recommended. This means that you have a system here, but you're not using a damping. You remember the damping when we put a damper like a cylinder, if you remember, with viscosity D or VF, or we use it in the spring and mass damper. In here, it means that your damper is not there. This is not a very good system. This is a simple harmonic motion. Okay? Now what do we have? We have here, instead of the 2, we change to 6. Now here, S equal minus 3. Both minus 3, minus 3. So both are minus 3. So when you have a system with 2 real and equal roots, this actually they call it critical system. This will have 1 minus 3t e to minus 3t minus e to minus 3t. So they are both e to minus 3t, but here this one we multiply it by t so that it will satisfy the differential equation that this system originated from. You remember, those all are originated from a differential equation. So these are the type of system of a second order system. We'll have critical. We'll have critical damping, they call it, no damping, underdamped, overdamped. Okay? So these are the system which we're going to deal with when we have a second order system. Higher order system will give you the same picture about its responses, but the rules and the theory and القوانين اللي راح ناخذها هي for a second order system, and higher order system are a different matter. We'll talk about it later. Okay. Actually, I was recording before this and talking, but I found out that it wasn't recording. So I repeated it, so it's all written because I didn't record in the first place. Now, second order system response معناته على هذا depending على هاي الأشياء اللي حكينا عنها, we'll have the following conclusion that we'll have system with reporting, critical, no damping, under damping, over damping. Okay, so I'll put a list of these and the meaning of each. First, second order system will have over damped response. We are talking about the natural because we saw that the force is a step one, doesn't change, it has no relation with the change of the parameters of the system. The natural response is changed by the parameter of the system. The forced response is changed by the step input or the input that is put on the system. So in this overdamped system, we'll have poles. The poles are two real, minus sigma 1 and sigma 2. Natural response will be in the form Cn equal K1 e to minus sigma 1 t, sigma 1 phi t, plus K2 e to minus sigma 2 t. And you saw that in the previous slide, which I was talking about. Now, 2, underdamped response, the poles or roots will be complex. So S, 1 or 2, will be minus sigma d plus minus j omega d. This is real, this is imaginary part, this is real part. So it will have real and imaginary. Once you see imaginary, then you expect to have a sinusoidal part in your response, and you'll have your system that is oscillatory. Natural response will be in the form A e to minus sigma d cosine افتح قوس omega t phi t minus phi. How he found those? We'll learn all this later through the example, and I show you everything. We'll understand this part first, and then we'll try to solve some questions. Okay. 3, underdamped response, poles are roots are undamped. Okay, this is undamped. This means no damping. Undamped response, poles or roots are S equal plus minus j omega 1. Okay, plus minus. واحدة plus, واحدة minus. Of course, you remember that complex roots, whether are like that one or pure, they come into pairs. Then the natural response will be Cn of t, n for natural, of course, which will be A cosine omega 1 t times phi. Okay, whenever you don't believe in this, look into this slide with the responses, which is I took it from your book. For critical damping, this is the last one we studied in the last slide. Roots are S equal sigma only. They are 2 real and equal. 2 real and equal roots. Okay, the response will be, of course, they are both the same, sigma 1 here, sigma 1 here. Of course, K1, K2, they are different. But here we multiplied by T. Okay, so we have 4 types of responses: overdamped, underdamped, critically damped, and no damping. Of course, no damp response is not very common to come across because it's not a very healthy response. So we prefer to have some sort of damping so that the system will be better controlled, not freely as it likes, because that will create some problem. Okay? If he give you like I'll go quickly into that skill problem just to show you. I'll solve problem later for you. Like skill assessment example or exercise 4.3. He's given you a g of s equal to 400 over s square plus 12s plus 400, and b 900 g of s, sorry, equal 900 over s square plus 90s plus 900, and let's say d, c, let's take them all. G of s equal to 225 over s square plus 30s plus s plus 225, and d g of s equal to 625 over s square plus 625. Of course, now I haven't given you other methods, only by factoring this. So if you go and factor, تاخذ denominator وتحلله. إذا طلع لك both real and unequal, it's overdone. Okay? Actually, أول one will be under. And B is over. And C is critical. And this one is clear. It has no حد وسطي. فهذا أكيد no damping. هذا they call it undamped. So you can try these. Only factor these. حللهم. حتى لو بالكالكوليتر تاعتك. I don't mind. Just try them. Okay. على التحليل. Here you will have because it's underdamped. You will have two complex roots, and here you have two real and unequal roots, and here you will have two real and equal roots, and here because we don't have the middle part like